Lewis, and this is Related Rates. So first we're just going to start with this nice simple example here. A rectangle is inscribed in a circle of radius r units. If the length of the rectangle is decreasing at the rate of p units per second, negative p, how fast is the area changing when the length is l units? So first, what I always like to do with related rates problems is draw me a little diagram. So I'm going to draw a rectangle inscribed in a circle. What else does this problem give us? We see that the radius, going to label that radius R. Do that right here. Also, we have the length of the rectangle, L. They also give us the rate of p units per second, which is the rate of the length decreasing. So we can call that dl dt, which equals negative p, because p units per second is decreasing. Now what are we looking for? How fast is the area changing when the length is l units? So we're looking for, going to call it dA dt of the rectangle. So how do we start this off? So I'm sitting here thinking to myself, how am I going to punish this problem? Pythagorean theorem. If we have r, we know that this entire length will be 2r. We also have this length right here. It's going to be L. And then we can call this length here a random variable. Let's call it W for the width of the rectangle. So first, we need to have a constraint equation. That equation is going to be the Pythagorean theorem. So L squared plus x squared equals 2r squared. So what are we going to do with this equation? We need to try to manipulate it in order to get to the area equation. We're looking for the area of the rectangle, which is A equals L times W. In order to get the equation in terms of one variable, I can manipulate my constraint to find W. So step number one, let's find W. L squared plus W squared equals 2R squared. W equals square root of 4R squared minus L squared. So now that I have this, I want to plug it into my area equation. A equals L times the square root of 4R squared minus L squared. Now where do I go from here? I'm trying to find dA dt. In order to do that, I need to take the derivative of the area. So dA dt equals, right here we have two different functions, essentially. So we're going to be using product rule. And also right here, we have a little chain rule because we have a function within a function. So we're going to get 4r squared plus L squared to the 1/2 dL dt plus L. This is where the chain rule comes into play. 1/2 4r squared minus L squared to the negative 1/2 times 8r dr dt. We are using a little bit of implicit differentiation in order to find dA dt. 2L dL dt. So first off, what can we simplify? We know that R is constant from the equation, from the problem. So you can cross out dr dt, and this entire unit right here, this is going to give us back 0. So that simplifies it down a little bit, so it's a little easier to work with. Now we have some known values. We know dl dt, so why not plug it in? So we're going to get here, and this all breaks down. We're going to get this. Now this is a problem on related rates, so I assume that you know how to do some basic algebra. 4r squared minus l squared to -1. So our final answer for how fast is the area changing when the length is L units is dA dt. Squared minus L squared. Right now I'm just cleaning everything up. We like everything to be a little crisp. Minus L squared. So our final answer. And take note that R and L are constants. Right now we're just working with them as variables. But in the actual real life problem, these are constants. And that's all we have.